Hello, my name is Murray Campbell, and this is the Pulse engine. It is a 3D game engine built on top of a framework called Azul, and it is my game engine. I've been working on it for the past few months. It features some really cool, good old game engine stuff. So, in a second, we're going to dive in, but I just wanted to showcase a small demo that highlights some of the current features. So you see here we have some camera stuff going on. We've got a player embodied by a model, bounding sphere collision. You can see that right there. And other assorted things. So I'm going to go step through this engine and highlight how this engine basically allows the user to do these things and to make games like this. So let's jump in. So the core of the engine occurs within this class right here called Pulse, and this is the class that basically initializes the game, loads all the resources, sets up scenes and decides what, tells the scenes to update and draw, and also handles the unloading of content within the engine. So there's that basically, and this is, I will go into these systems, but right now I want to look at how the user, I want to start from the top and look at how the user uses the engine to make games. So let's take a look at this frigate class. This is the ship that you saw moving around before. So to allow the user, this class to register for update, draw, alarm, input, and collision callbacks, all we have to do is inherit from these various classes. So we have updatable, drawable, alarmable, inputable, and collidable, and by inheriting from these, we gain access to these functions that let us register for these various services within the engine. On top of that, the user defines an on-scene enter and on-scene exit function for obviously when the object enters the scene and exits the scene. The functions that it uses, that it registers for, are defined here in the header file as well. We can store some other values that game-specific values for use within those update and draw and all of those callbacks, and all of those functions, and then we also can define objects and models. And so so when the user creates this frigate object, they basically take those graphics object variables and can pull from these managers, these asset managers, to basically get assets from their resources folder. Let me take a look at that actually. It's in the assets folder. You can have different subfolders for images, models, textures, and shaders. And these asset managers allow the user to get these assets from the from the managers. So first important thing to note, these asset managers allow the user to load and get resources. So there is a class that the user must define called load resources, and in this is where the user will load all of their images, models, textures, shaders, and such. In here also we set the first scene, but we'll talk about the scene system in a second. So let's take a look at these asset managers. I'm just going to show one because they function more or less the same. They have a load, get, and delete function. Essentially, they basically just like pull a model, which comes from Azul, into pull it from like a file path, and allow the user to access it with a get and with like a string that they set themselves. So they get these resources. They set their other values like position, rotation, scale, which they can use to this in this case gets modified in the update, and then they set the world there. This user also is registering for collision, so the frigate class has to set the collider model, which basically means getting the model from this object, this graphics object variable that we defined before. And then also here in the frigate, I set up that camera that you saw earlier. So in the on-scene enter function, on-scene enter is where the user will typically register for various services within the engine. This is where they call update registration, where they'll call like draw. They'll register for all of these things here, like key events and alarms and such. Also, collision registration is done here as well. Here's the update function. It's pretty simple for this. Essentially, we are creating a world from the scale and rotation and position, which are modified in other functions in this class, such as key event, like key events and such. We update the collision data based on this world, and then there's some other God camera stuff here. In the frigate draw class, it tells the graphics object to render to the current scene. Game objects will have a pointer to the current scene, which they can call to do things like get the current camera and such. I also have a visualizer class for the bounding spheres, which is those blue spheres that you saw, and you can call the render bounding sphere function in your draw function to basically render a sphere on that model's bounding sphere. It is just a visual representation of the model's bounding sphere. Here in the alarm function, we just do some arbitrary debug messages, but you can do whatever there. Then we have these key events, and this is where we're doing things like checking for input and then modifying values like the position and the rotation. This is also where we do the camera stuff. When the scene exits, or when the frigate leaves the scene, that is typically when we deregister from everything that we registered to before. Which reminds me, I need to deregister for these God camera controls. That's important. And then any pointers are deleted in the destructor for the class. So there is that. That's how that works. So now, one other thing to mention is, I forgot to show this, but when I press a button here, it will change the scene, and in this scene you can see this is basically the scene without the world plane and a sprite that is rendered on top of everything. This is just to highlight scene changing in the engine and the sprite functionality. So there's that. Let's take a look here. So yeah, there's like how the user typically interfaces with the various systems in the engine currently. Currently, the engine only has support for bounding sphere collisions, but other collision types will be on the way soon. Okay, let's talk about scenes for a little bit and how the user defines scenes and all of that fun stuff. Scenes are a little bit simpler. Basically, you will in the header file, you'll define all of the objects that you are using in the scene. You have to, when you inherit from scene, there are two functions, initialize and end scene, that you should override. You don't need to define a constructor for your scene. That should be done in initialize, which is called when the scene is loaded when it is the current scene, when it becomes the current scene. So here we're basically just creating these objects and telling the engine to add the objects to the scene. After that, we set collision pairs if we want collision within the engine between certain objects. You can set a collision pair, or you can set collision to oneself. An object will register collisions against objects of the same type. And then the end scene function, we clean up all these pointers and do any other deletions. I have a factory for those bullets, and I tell the factory to delete here. So that's typically how a scene works. It's pretty simple and pretty easy to use, which is really nice. Okay, let's move on. Here there is a class called initialize GAM. This is where the user will do not non-game specific stuff that's still important, like setting the name of the window, setting the width and height of the screen, the clear color, all that fun stuff. This is just like a few basic functions that we can use to set things like that. Okay. So now that we've kind of taken a look at how the user interfaces with the engine, we can kind of have a better idea of how, or a better jumping off point for these other systems. So I talked earlier about the asset managers. Those are clear. They basically load and get materials, textures, other assets, various assets. I'm going to talk about some other managers that the user has access to. We have a camera manager that manages the current camera and scene cameras for the game. It's relatively simple. And then we also have a time manager that allows the user to get valuable time information from the engine, as well as freeze the game, freeze the current frame and step through during gameplay. So if I can take a look at that, that's so when I press the P button, it pauses. Let me actually shoot something. Yeah, see? So now when I press the O button, it steps through frame by frame. And that's that. Okay, so let's see, the camera manager. Okay, so we got these managers out of the way. They're good. Let's see, what else can we talk about? Let's actually go into the class diagram. Yay, okay. So, I mentioned these asset managers before. Let's talk about the scene manager. This is basically what the main engine file calls to tell the scene and all of the objects associated with that scene to update and draw, which is really important. Okay, so let's take a look at Scene Manager. So the scene manager manages scenes. It also handles things like scene changes, which is done with set next scene. We have add to current scene, which is basically called in the scene. The scene can access or call its own add to scene, adds a game object, which passes it through the scene class into the scene manager to add to the current scene. The scene manager holds a reference to the current scene, and this is where that lives. That is where the current scene lives. It also has a scene change broker, which is basically a command pattern that allows the offloading of like scene changes. So there's that. Let's see. We can take a look at. So here's the update function. In the update function, we check to see if we need to execute any scene change commands. This happens before we tell the current scene to update, in case in case the user just told the engine to change the scene. Then we also tell the current scene to draw in the scene manager's draw function. These are all called in pulse.cpp. And then when the scene manager is deleted, we end the scene. But the scene can be ended by changing the scene as well. That also happens there. So let's take a look at the command structure that powers scene changes. So we have this. We have these commands that allow the user to remove and add game objects to the scene. They're relatively simple. They just call that game objects on scene exit or on scene enter function, as well as they set the scene pointer for that game object so that the user can access the current scene from that game object. In the set next scene command, basically all that does is it ends the current scene. It ends the current scene and sets the current scene to the next scene, whatever is defined when that command is created. And then after that, it tells that next scene to initialize, and that's when the initialization function is called during scene changes. Let's take a look here. We can take a look at the scene change broker. Basically, all that does is it holds a list of commands. Let's see. I might actually benefit from changing this to a set. I changed a lot of my lists to sets, but I guess I didn't do that for this one, so I should definitely put that on the list. This basically, tells it has various things that allow you to add commands and execute those commands. And those are called, as you saw before, in the scene manager. So there's the scene change broker. The scene registration broker is pretty much the same. Okay, so now that we talked about that, we can talk about scenes themselves. Scenes. Here, let's take a look. Scenes have a lot in them. They just basically define functions that allow the user to add objects to the scene, remove them from the scene, and they also pass through various. This is where like registering for various services sort of lives. The user, when they when they call a registration function like update registration, that basically passes through to a function that tells the current scene to register for like that particular object for update or whatever service, and you can see in there it creates a command and sends it to the scene registration broker to be executed to allow that object to register for whatever service Here you can kind of see that in here. The scene has this reference to the registration broker, and the registration broker is what tells all of these commands to execute. That happens particularly in you saw earlier in the scene manager. It tells the current scene to update. In the current scene's update function, we have a very specific order. We tell the registration broker to execute those commands first before we tell all of the services to execute. This is basically so that anything that needs to be registered is registered before any services are called, so that those guys can get their update right away. After that, we tell the services to process their elements, which is basically like calling update or calling the alarm. And then we tell the time manager to process the time after all of that, because that's kind of independent of registering, of game object registration. Let's see. So you can see the scene has references also to these various managers. You can see these down here, apart from the scene registration broker. We have references to the various managers. These are not pointers. These are basically, we just need these to add commands or no, that's not what we need those for. Yes, we do. We need those two as references for commands. So these managers live here, basically, in the scene. And yeah, so that's where those live. Also, for collision stuff, you can see that here. Collision is basically the same as any other registration. It's just a little bit more complex because it is templated to allow the user to register for collision between objects that they define, rather than just like collidables, because obviously collision is going to be different between objects. So there's scenes. Cool. That's great. Let's see, what should I talk about next? So we've kind of talked about scenes. That's all well and good. This is kind of independent. I want to touch on game objects and stuff and the related stuff last. So let's talk about sprites quickly. Sprites are basically an object that wraps around Azul's image class and offers the users some extra goodies to interface with. There's a sprite manager that the user can call as a sprite if they define a sprite to get the there's a sprite camera, which is it handles this orthographic sprite camera that gets defined and set here, so the user doesn't have to worry about anything like that. They can just call the sprite camera and render a sprite on the screen. I have a class here that does that. It's basically a game object that registers for function or for various services in the engine normally. Okay. But instead of using graphics objects, it uses this sprite class, gets an image from the image manager, and defines a rect that encompasses its its thing. The rect is the position values, x and y values, and then the width and the height. Here we just basically rotate, stitch around. And then here in draw, we're telling the sprite to render using a camera, but we don't want to use the scene camera, we want to use a sprite camera. So the user calls the sprite manager's get sprite camera function. Sprites are really cool, they're easy, all that good stuff. So now we've detailed pretty much everything except game objects. So let's begin down the long road of game objects. Game objects, the game object based class just has some basic functions that get passed through for the user to use. They can tell a game object to be marked for destroy or scene exit. They can tell there are these virtual functions for unseen enter and unseen exit. I talked about those before. We'll look at those. There's a protected pointer to the current scene. This is how the user gets things like the camera and all that fun stuff. There's also a private function called setScenePointer that is only called in the command. We don't want the user to use this setScenePointer function, so that's there. In the gameObject.cpp file, we define the mark for scene exit function. That basically tells the current scene to remove this game object from the current scene, sets the current scene value to null. Yeah, this is all pretty basic. It's self-explanatory. This is also in this folder we have the game object. There's a base command class for deriving commands from. The user probably doesn't need to do this, need to use this, but they can. It's basically just a base class with an execute function. They define the execute function themselves, and they can handle their own they can make their own brokers to handle the lists and register and all of that if they need to. So here we have okay, so the user can so the user doesn't actually inherit in their game objects. They don't actually inherit from the game object class directly. They rather inherit from the components of the game object that they want, such as updatable, drawable, alarmable, all of that stuff. Rarely will they just inherit from game object, because then it doesn't do anything. If they want something to be drawn on the screen, they need to inherit from drawable. If they want something to move or do something that requires an update function, they need to inherit from updatable. So all of these, all of the registration systems for these various ubbles basically works the same, except for collision. I'll talk about that later, but I'll basically just talk about registration for that once. We have these commands that basically tell the various managers of these ubbles to register and deregister them from the current scene. If you see in the updatable manager, there is a register and deregister function. The updatable manager has a list that it holds. These are sets, so that we can use sets so that there are unique elements, and we don't have to have any duplicates by default. And in here, there's also a process elements function. You saw that earlier in the scene class. Process elements is called in each of these managers, and that basically iterates through all of the list of whatever object and calls the function that it needs to on them, such as update or draw. Here we have the updatable class, which inherits from game object. These are what inherit from game object. They basically define the update function, the virtual update function that the user defines, and then these registration functions that allow the user to register to the current scene. Drawable works exactly the same as inputable, except it calls for draw. Another important thing about the draw class about the drawable class is that the user has to define a drawable type. This is because models and sprites are handled differently. So that's basically when they register register the object to the current scene. There's basically like a draw order thing so that's why we need to define the type. So the user defines that type, and then it tells the current scene to register for that type. The commands work the same. That's good. Inputable is a little different. We can look at inputable. We have these functions that the user defines, such as key pressed, key held, key released, and then the various registration and deregistration functions. We have this enum for the input event type that the user defines when they want to register for a key event. They define this input event type, so if they want a certain key, they want to listen for key presses of the K key, for example, they'll use this. In the inputable CPP, we just have these registration definitions. That's all well and good. Here, things are a little different. When the user registers for a keyboard event, a key event handler is created. And these handlers, essentially what they do is when they're registered, they register an inputable, the key event handler holds a couple lists, sets. It holds sets of key presses and key releases for a certain key, and then it listens specifically to for that key in its monitor key events function, which is called in the key event manager. Here we see it's iterating through the key presses, and if the key, don't need to go too into detail for this. It's basically like that. Then the keyboard event manager. We have a set of key event handlers. And this is defined, this is held in the scene that you saw before. So this registers and deregisters stuff. Key event handlers, or inputables. Yeah. So it registers inputables. You saw that before. And then we have stuff to find the handler with key. This is needed here in case there are duplicate handlers, although it looks like we might not need that. I can't think right now. And then process of elements, it basically tells the various handlers to monitor the key events, and that's how the listening system happens for that. The commands for this class are what you've seen before. Then we can talk about alarmable. Alarmable is a little different. We have 3 different alarm IDs the user can register for, so they can have 3 different alarm functions. I can expand this in the future if need be, but right now there are 3. The user defines these alarm 0, alarm 1, alarm 2 functions, and then does whatever they want when the alarm gets called. When they register for a certain alarm ID that they then define, and then define a time that they want that alarm to go off. The alarmable also has a dispatch function that basically tells it takes in an alarm ID, and then depending on the alarm ID, it tells a different alarm to get called, basically, and then it deregisters that alarm. So alarms are registered, and that's when the timing starts. When that time runs out, the function is called, the corresponding alarm function is called, and then it's deregistered. It's basically setting and stopping an alarm. The alarm manager is what you've seen before. It has this map. Actually, it's not a set, but it's a map because we need the time. So it's a map of alarm markers. Alarm markers basically are a class that has the time in them and checks to see. Well, alarm markers basically hold are what the manager uses to call uh, whatever event, the whatever alarm function in the alarmable when the time is out. So you can see that here in process elements or process alarms. if the time that we get from the time manager is greater than or equal to whatever the time that we set for that alarmable, we then tell that alarmable to call the event. So that's how alarmables work. That's good. So this is everything in the game object folder. Another thing that the user can register for is collisions, and this is a whole huge fiasco. Okay. So, earlier you saw how the user interfaces with this class. It's basically like in the scene, they register, they basically set various collision pairs that the game engine tests for, or collisions between same game objects. In the game objects themselves, they register for collision of that object and then deregister when they leave the scene or whenever they want. And then they have the collision callback that in case they want to do something when something collides, when they collide with something, or whatever they set, or whatever they were checking for collisions with, whatever other object that we're checking for collisions with. So you can see that virtual function there. Collidables have a model that pointer to the model, or they have a bounding sphere that they hold. And these are important, especially the bounding sphere, because this is needed for invoking the visualizer to render the bounding sphere that we saw earlier. We have the various collision registration functions, and then these collision test functions in the collidable. These are called in the scene, but they are passed through to here, I believe. Yeah. So, let's see. We also have this update collision data function that is called an update of a collidable, or in start if it's not moving, if it's not updating, that basically updates the collision model matrix for that object, which is important. So there's that. We have a collidable group class. This is basically created whenever we set collision pair or set collision self. We create this collidable group. It's a templated class that passes through registration, deregistration. Sorry for the beeping. I'm in San Francisco. Okay, it stopped. Cool. Yeah, there's that. It's a singleton? Yeah, it's a singleton. Or a multiton, I guess. So, let's see. Collision manager. Yeah, we've got this collision manager. It's a scene level manager. When the scene tells this manager to process its collision tests, it goes through its various collision test commands and tells them to execute. So these test commands are where the meat and bones of the operation are. So we have these various base collision commands. I just define these to separate them from the base command. These are collision command and collision group command. collision shutdown command, and collision test command. Well, collision shutdown command is its own thing, but collision test command inherits from command. Collision group commands inherit from this command. Collision commands. You'll see. I don't know where some of these are going right now, but yeah, do go somewhere. What's important about these are these collision test pair and collision test self commands. In their execute functions, when they're executed, we iterate through basically these collections. We have collections of these collidables. Each collidable group has a basically like a collection of of like the collidables that are registered to that group. So every time an object registers for collision and sets a collision pair, a different collidable group is created for that object. So there will be a collidable group for the frigate, a collidable group for the cottage, stuff like that. Oh, my throat is dying. So in the execute function, in collision test pair command, we were iterating through those collections, looking through each one, and if we test for collision. I'll talk about that in a second. And if that test comes back positive, we call the collision function in each object. In the collision test self command, we do the same thing, except for it's for one object. We also check to make sure that the objects that we're checking are not the same. And if they're not the same, then we test the pair. We basically call this collision test pair function. But it's the same, they're the same type, but it's just handled differently. If the test comes back positive, then we call collision functions in each of those objects. So let's look at collision test pair. That function is important. I should also mention quickly before that, the bounding sphere class. This is important actually because this is basically like the bounding sphere of the model, and this is what we use to check for collision. The compute data function is called every time we tell the game object to update its collision data, and this takes in the model and the it's the transform, rotation, scale matrix. So in there we set the center and the radius of the bounding sphere. This is really important. Also here, you're going to see in a second, we have this intersect function which calls the intersect function in a math class. This is where we are using math to check for collision between two spheres, given a center and a radius for both spheres. So we talked about collidable before. We have this set collision test pair function, static bool. When that gets called, we tell the bounding sphere in the collidable to call the intersect function, which I just talked about. So we do that. That goes through to the math tech class. So let's take a look at that quickly. It's in tools. Here we've got this intersect function. It's a singleton. It basically does this math and returns true if the bounding spheres are colliding with each other. Also important to note is the visualizer class. The visualizer class currently allows a user to render a bounding sphere. So the user passes in the graphics object's bounding sphere, the game object's bounding sphere that we have. Because when we inherit from collidable, we get a bounding sphere. And then we also give it a color value. So it renders this bounding sphere. That's all good. That happens in the draw function of an object. Cool. That's pretty much it for collision. What else is there to talk about? That's pretty much it right now. I've talked about scene changing. I've talked about this stuff. I just want to check to see if there's anything else before I talk about the documentation. So let's take a look at the class diagram. Yeah, this is all well and good. These are the various systems that I've talked about earlier. You can look at this if you need to, but I basically explained the structure and flow of all of this just by talking about it. So yeah, this is the Pulse engine. On top of all of this, we have a developing documentation website that details what the engine is and gives the user access to all of the useful classes that they can use. In the modules section, this is the important part, we have information about the specific user interface stuff, like all of the stuff that the user is going to be interfacing with when they use the engine, the really important stuff. You can see in all of these there's detailed explanation for how each of these work. These asset managers are relatively fine. These GAM object modules are really important. You can see each one has a little bit about it. Yeah, you can see some of these classes have some important information of like how you use them. You can see that here, like alarm registration, tells you like what you need to define, all of that. It's still developing, there's stuff that I still need to add. Yeah, we got these unseen enter functions, all that good stuff. The tools, scene stuff. I still haven't added sprite stuff. Here, this is a cool thing. I've got all of this stuff, and you can see like these functions in use. We also have the demo that the user can look through. Yeah, this is still being worked on. It could use a little bit more, but that's a job for next quarter. But yeah, I'm pretty sure this is basically it. I think something that I like definitely need to do at some point is just go through my engine, like spend a day going through my engine and making sure that everything is being unloaded correctly, handled correctly. If I'm setting up pointers, I need to delete them. You saw earlier that I wasn't deregistering from that from all those key events that I registered for in the God camera for the frigate. That's bad. I need to fix that. I showed you documentation. There's yeah. Okay. Cool. That's pretty much it. Thanks for a great quarter. It's been really fun. You can see what I talked about in the questionnaire. I go into a little more detail about how it felt. But all in all, it was like a really good, somewhat empowering quarter. It felt like really good to be able to tackle these problems so manageably. It was a very challenging quarter, but I had a lot of fun, and this is actually like work that I really enjoy, and I wasn't expecting to enjoy working on game engines this much. So I'm excited for next quarter. Right, that's pretty much it. We've had fun. Thanks for everything. I'll see you later.